So, one thing we're going to do is we're going to develop a shortcut to the limit definition of derivatives. So, let me see if you guys can help me. Could everybody write down the limit definition derivative on your, whatever you're taking notes on? Just write it down for yourself. Try not to look it up. Just try to write it down. Let's see if we all get the same thing. So when I say definition of derivative, that means what you guys are writing down. We are going to use the limit definition of derivative a few times. Besides the final exam, I'm not going to make you do the limit definition again until the final.
Yay!
But we will see it because we're still going to prove how many functions do we not know how to take the derivative of yet? A lot, right? Basically all of them. We haven't really developed a rule for anything yet. Yes? So instead of doing limit definition for every function as it comes, we're going to develop derivative rules for families of functions. For example, the first one we're going to look at is polynomials. Every polynomial is essentially the same thing, just higher degrees, right? Different numbers and different coefficients. But they're all essentially the same damn thing, yes? You guys understand? They all have the same way of being built. And then we can look at like exponentials, and then we can look at logarithms, and then we can look at trig functions, right? We're going to kind of do one at a time and try to develop shortcuts. So, let me catch up to you. So hopefully in your limit definition of derivative, you have a limit. And what goes on the top?
F.
And what's this idea come from? This the body of it. What's the idea behind this? Slope. And more directly, y2 minus y1 over xi. Output 2 minus output 1 over input 2 minus input 1. Yes? And there's only an h down there because x plus h minus x is h. So, right? So you just keep reminding yourself, this shit is built on stuff you know really well. It's built on that. This dude freaks some of us way out. But that's a little dude we talked about all by himself, and this is one way we can use his help. Okay. So, do you remember 21st? No. This guy. No. You never, I'm not going to force you to use it ever. I showed it to you because it's really useful. I'm going to use it to prove something, and then we're going to be able to take the derivative of any polynomial. In fact, we're going to be able to take the derivative of anything that has terms in the form x to the power. Anything. And we're going to start with Pascal's triangle. It's going to help us out somehow. Okay. Does somebody remember, in the context of multiplying shit out, what like this row was related to? Second?
Was it a plus b to the second?
Good, yeah, so like this would be something like x plus h to the second power, right? Or anything, like a little binomial to the second power, these would be the coefficients of the answer, yes? X plus 1 squared is x squared plus 2x plus 1. X plus 1 cubed is x cubed plus 3x squared plus 3x plus 1, yes? On one level, that's insane. But on another level, this thing is built by adding things before, and how do you FOIL? You start, when you multiply, you start to combine like terms. Combine things based on what was there before. So that's, on at least the surface level, why it makes sense this is related. Okay, maybe. Now, see this number here? See this number here? You with me? So if I went down far enough, if I had to do x plus h to the 17th, yes? There would be a 1 first, yes? What would be next? 17, yes? Is everybody with me? You see the pattern. It's got to be. If that's a 1, that's a 3, then next would be 1, 4, next would be 1, 5, and 1, 6. And of course, when I get to the 17th row, it would be a 17, yeah? Or the row that relates to the 17th power. Is everybody okay with that? The squared row had a 2. The cube row had a 3. The 4th power row, 1 plus 3 is 4, right? So that second number in is always going to be 1 plus the number that came before. It's always, and that number is always going to be related to the power. It's just the pattern of the Pascal's triangle. Do you guys see that? So again, one more row. Is everybody cool with this? Put a 1 on the outside, 1 plus 3 is 4. And then other shit. And this would be related to x plus h to the 4th power. So it's a 4th power. The second number in is a 4. I'm hyper-focusing on something that's going to become very important in a minute. Does everybody get just that?
So does it grow at all, or you?
Hell yeah. So again, this whole row, 3 plus 3 is 6. 3 plus 1 is 4. And then a 1 on the outside. Then the next one will be 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And then a 1 on the outside. So every row grows because it adds the 2 and it puts 1 on the outside, right? Adds the 2 above and put 1s on the outside. So on one level, this is just some bored dude. Before we had freaking anything, iTunes, we didn't even have Atari back when they made this. So he was just bored. He's like, let me play with numbers. 1, 1, 1, 1, 2. That's interesting. Let me just keep adding. And that was a good time. It's raining outside. Had his candle going. Like, let me play. Ooh. Okay. Sorry. I'm not going to make fun because I'm the little kid that was playing with the calculator in the corner. I wonder what Jeff's going to do. All right. Is everybody semi with me? If I FOILed this out, do you want to? No, but if I did, it would be 1x to the 17th plus 17x to the 16th h plus blah, 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 blah. I know what the first coefficient would be. It would be a 1. And the second coefficient would be a 7 frickin' t. Yes?
So technically you will know the last two as well, right?
Say again?
Technically you will know the last two as well.
Of course. They would be the same because of the symmetry. Yes, exactly. For some reason, I don't care about that. You'll see in a minute. I just want it. Is everybody really there? Like you said, and like Jason pointed out, there's more to the picture, and you could make every row you want. I'm just focusing on these, and you'll see why. Okay. Can somebody tell me then, what if I had x plus h to the n? What would the coefficient start with?
X to the
Of course, it would be a 1. What would be next?
X to the end.
No, I mean just the coefficient. N. Yes? What was it for the 3rd power? 1, 3, other shit. 4th power, 1, 4, other shit. 5th power, 1, 5, other shit. 17, 1, 17, other shit. Nth power, 1, n, other shit. Yes? Okay, is everybody with me? Okay. That's a consequence of how Pascal, who was bored one day. This is not the real story, but it's more interesting. And Jess was there. Oh, good. Okay. So if you, all right. Therefore, if I wanted to figure out the rule, the derivative of everything that could be written as x to a power, can you guys help me? So again, I'm not going to make you in a test or quiz until the final do limit definition again, but we're going to use the Chev in lecture. Because you have to prove where these forms come from. Could you set up for me, please, the limit definition of the derivative to figure out f prime for that? You just wrote it down earlier. Now I just want you to do it for this guy. Just set it up. Don't go any further. Just set up with the limit h go to 0, blah, blah, blah.
For x to the n?
Yep, that's our function, x to the n. So we wrote this earlier. instead of doing x squared, and then we'll do x cubed, and then we'll do it. No, we're just going to do every frickin' thing we could all at once. If I do that, I've done every x to a power. Okay. So what is f of x plus h?
X plus h to the n.
Yeah. Interesting. So then this would be the limit. H goes to 0. X plus h to the n minus x to the n over h. Is that cool? Yes? Now, if I would have started with this, by the way, I'm well aware my little n's look like h's, which is bad, I'm sorry. I really should just capitalize my n's or something. Make this like really low there. Stove pipe H. Okay. If I had started here, we would all freaked out a little bit because not only do I not want to do, how would I do it? How many x plus h's do I have? N. How many is that? Whatever n is. But now I have a way to rewrite this shit, or at least the first couple of terms. So let me see if you guys are really with me. How do I start to rewrite this? We just figured it out a second ago. It would be 1, all x's, yes? Coefficient of 1, and then all x's. Plus, what would the next coefficient be? We figured it out. When it was 17, it was 17. When it's n, yeah. So I'll have n, 1 less x, 1 more h. That's how that kind of works, that rule. Yes? Let me stop for a minute. The other terms, every other term, like the next term, is going to have weird shit here. 1 less x, 1 more h. Do you see how every other term after this one, every other term after that one has at least 2 h's in it? Do you all agree? In fact, how many h's will the very last term have? N. It would be h to the n at the end, yes? X plus h cubed has an x cubed at the beginning and an h cubed at the end, yes? So does everybody see? The very first term has no h's. Second term has 1 h, third term has 2 h's. Every term after that has at least 2 h's. Why is that important? I don't know. We're going to find out. Because, of course, what's on the bottom of this ship? H. So then it becomes important. What stays alive, yes? Yeah. What have I forgotten here? What's at the very end? Minus x to the n. So these cancel, yes? Get out of here. Now you guys have done, hopefully, enough of these that you know that had to happen. Especially when we're working with polynomials, everything without an h should cancel. So then I'm able to do what now? I can divide everything by h. So what happens here? They cancel. So I'm going to get n x to the n minus 1. These h's cancel. Is that cool? Plus shit x to the n minus 2 h. Yes? H squared divided by h is h. Plus other shit that has h in it. At least h. H squared, x cubed. And what is h approaching? What are we letting h approach? 0. So then what happens? What happens to this term? Goes to 0. What happens to every other term after it? So what's the answer? nx to the n minus 1. That might look kind of weird. I know some of you guys have taken calc before because you were using this rule on the test, which you don't know officially, so you can't do that shit. So if you've taken calc before, don't be pulling out stuff like L'Hopital's rule early. That ain't good because you don't officially know it. This actually jives with something we noticed before. So watch what this does. Let me write this down. You ready? Has everybody got what they want from this? By the way, I have a handout that's actually got this kind of written up. A computer did it, so then you'll be able to read it. Well, I typed it, I should say. I did say computer. So now we figured out f of x equals x to the n, f prime of x equals n x to the n minus 1. So what is a shortcut way to say what happens to x to a power? The power looks like it comes down, and then it goes down by 1. So before I do what I'm about to do, let's try a few of these out immediately. So what if I had x to the 70th? What is the derivative?
70x.
Yes, the 70 comes down. 69 power. So what if I had x to the negative 2? The negative 2 comes down. X to the negative 3. Kick ass, yes? This is the best rule. The best rule. If you have x, now, I don't know if anyone's concerned about this, but the whole Pascal's triangle can be extended to non-whole number powers. There's an extension of it. That's why I can do like a negative 2 power. I could do like a 1/2 power. So what would it be if I had g of x equals x to the 3/7 power? What would the derivative be? 3/7 x to the almost?
Negative 447.
Yes. So real quick, what always happens to the power? You got to take 1 away. Yes. All right. Now listen. Stick with me. I'm going to show you a nifty little shortcut. It's going to be really useful because you got to do a lot of this shit. You're going to do a lot of this shit. So this little tiny shortcut is going to help out a lot. I've got to subtract 1. How do you subtract 1 from 3/7? Well, it's 1 over 1, correct? Then you got to multiply by 7 on top and bottom, yes? So you end up doing 3 minus 7 over 7. So don't do any of that shit. If I'm going to take the derivative of something with a fractional power, you do top minus bottom over bottom. Because that's what you would do anyway. What's 3 minus 7? Negative 4, and then you just put it back over 7. Okay. I'm going to really push my luck. Where'd that function come from? I pulled it straight out of my head. Yes? It could have come from anywhere. I just wrote it here and we did shit to it. Is this a function? Is this a function? Is this a function? Yes. It happens to be the derivative of something else, but so is this. This is the derivative of something else too. We just didn't start there. I need you to understand this. This is a function, correct? Couldn't I have given you this and then we would have taken its derivative? All right, so let's take another derivative. So what do you think is going to happen? I'm going to have 2 of these stupid little dudes, yes? G double prime. So G double prime. So look what I do for myself. Any number just comes for the ride. So I kind of do this for myself. 3/7 is just sitting out there waiting because this is the guy that's going to have stuff happen, yes? How do I take the derivative of this guy? Yeah, the negative 4/7 comes down. Negative 4 minus 7 is? Negative 4 minus 7 is? Negative 11, and you put it back over 7. And then how do you clean that up? Yeah, negative 12 over 49, x to the negative 11/7. Shabao! Shabao! How long could you keep doing this? Well, theoretically, forever. In reality, maybe 2 more times, Joe. No, we're not going to do it. But do you understand? Anything you take a derivative of, you could keep going if you needed to. In this class, in the future, we're going to talk about what these higher derivatives mean. For example, do you guys know what velocity is? We talked about this before a little bit. It's the rate of change of something over time. Position. So if I'm here, and then 2 seconds later I'm over here, I can see how far did I go divided by 2. So rate of change of position. So it's the derivative of position. So ready with me? You might never have said that before in your life, but does it make sense now? What's the slope, which is the derivative? It's just the rate of change. What's acceleration? If you accelerate, what are you directly changing? Your velocity. So it's the rate of change of velocity. So it's the second derivative of position. It's the derivative of velocity. Yes? So we've used first, second derivatives all the time in our lives. We had no idea we were. You guys are all with me. Velocity. If my velocity is set to something, my position is changing. If my acceleration is set to something, my velocity is changing. Yes? Okay. Awesome.
So the first derivation in this context would be the velocity.
Yeah, if this was the position of a particle.
And the second one would be velocity.
Velocity.
And the second one would be acceleration.
Acceleration. Kick ass.
Okay.
And the third one, just to let you know, there's a third one that has a physical. I had a car, my first car was a little 84 Dodge Charger. And that thing was awesome. But later in its life, it did this kind of thing where I'd hit the acceleration and go, and like, yeah, the thing was like, should I go? Sure, I'll go. And so the third derivative is the change in acceleration. And what we feel when the acceleration changes is a jerk. So the third derivative, oh, you knew that? I should have asked if
We're
anyone.
looking at physics, so it's like.
Oh, there you go. So the third derivative is called the jerk. Yes? And you're like, finally, math. Yeah, it's a jerk. All the shit's a jerk. No. That is officially the jerk. Okay. How you guys feel about this little dude just by himself? This rule we just developed. It's one of the coolest kick-ass rules. Love the hell out of it because there's gonna be more rules coming. So let's throw some other stuff on here. What if I had this function here? Okay. Derivatives are always based on what process? In the background. Derivatives, all right, that's a weird question, but what's the only way that we know to directly get the derivative of a function? We have to apply the limit definition, right? You guys with me? If I did the limit of this whole thing, wouldn't that be equal to the limit of this minus the limit of this? Yes? If I said, what's the limit as x goes to 3 of x squared plus x? Wouldn't you just plug a 3 into x squared and a 3 into, you would do the limit of each thing individually, yes? And then add them together. Since derivatives are based on limits, you can kind of think of it as distributing across plus and minus. So if I wanted to do this guy's derivative, number one, which piece of this should I do something with before I try to take the derivative? Yeah. So if any of you guys have ever had me before, you might have heard me rant about I wish root notation didn't exist. It's the dumbest decision it's in contention for the dumbest decisions in math history. How do I rewrite the cube root of x to the 5th?
X to the 5th to the 5th.
Yes, I write it in the form it should be in. X to the... Good. How do you remember that shit? Easy. What's on the bottom of most plants? In the ground. Roots. So the root goes on the bottom, the power goes on the top. It's powerful. One semester I did that. That's why I gotta say most plants now, because I said what's in the bottom of plants, and somebody back was like, technically tubers are about, shut up. Most plants, just to cut off my botanist nerds out there, have roots on the bottom. Yes? So that's how you rewrite that. So how do you take this? No, notice. Why didn't I put a prime here? I haven't done a freaking derivative yet. I just rewrote what I have to work with. Now I'm gonna take a derivative. So how's this work?
5/3.
Yep, 5/3. X to the 5 minus 3. 2/3. Minus?
21.
Good. 7 comes down. There's already a 3.
Next to this.
Next to the 6. Kick ass. Kick. Is everybody feeling okay? You have to like this. You have to. This is such a great thing. If you can put it in the form x to a power, the best rule ever applies. Yes? Well, it's the second best rule. We'll see the best rule. What about this? Here's something a little bit different. J of x, not just because of the j. What do you got, Jeff? 1 over the 7th root of x to the 13th minus, you could do it, Jeff, 4x plus 2. Yes. Try to do that. Oh, there we So of course, I'm not going to put a prime yet. There's two things to worry about here.
X to the negative.
Good. So this by itself would be 13 over 7, but you need a negative because it's been flipped. It's on the bottom. And then minus 4x plus 2. Now, derivative. So there the power
Negative 13 over 7.
comes down. Negative 13 minus 7 is
Negative 20 over 7.
negative 20.
Minus 4.
Yes! What's the power here? 1. So the 1 comes down. X to the 0. What's x to the 0? 1. Now, what about this guy? What's the power on the x? Good! 0 comes down. Whole thing goes to 0. I don't give a shit what else happens. It's 0. Yes? Another way to look at this is this whole piece right there. What is that? If you graphed it, it would be a... Taking the derivative is finding the... So this whole piece should just have a negative 4, yes? Because what's the slope of this? Negative 4, so don't forget. Taking the derivative is finding the slope. So if I'm looking at a linear thing, I don't have to do any calculus. I'm just like, what's the slope? I'm going to write that shit down. So this piece, all it contributes is minus 4, because that's its slope. Or you can do it each piece's derivative. You just have to be more careful. So if I ask you, well, this is not the best function to ask you. Well, sure. If I ask you, what's the output for j if x is 1? Where would you plug 1? Huh? Where would you plug 1?
In every X.
Say again?
In every X.
But there's a lot of x's up there. Where?
The last.
No. What's this function tell me?
Oh, you want to
Slope! If I said what's the
Original.
slope of j function at 1, what would you use?
the prime.
J prime. If I said what point,
So you
where
wanna use the
is j
original.
for an input of 1, you would use this guy.
The original.
This is why don't put a frickin' prime unless you're actually doing a derivative. Because we are going to get to a point where we have problems and I have to know which thing to plug what I'm looking at in. We are going to look at second derivatives and they're going to have a physical meaning. Not just acceleration, but like a graphical meaning. So sometimes you have to use the second, sometimes you have to use first, sometimes you use the original, yes? What's the original do? Gives me points, tells me where the function is. What's the first derivative do? Slope. Second derivative we got to talk about later. But we'll figure out what its physical interpretation is. Okay. What its graphically physical interpretation. Yes?
How do you get the two to cancel out?
Do you agree that if it's just 2, it's got no x's?
Yeah.
So x to the 0,
Oh yeah.
right? And then how do you take the derivative? 0 comes down, and then I can just stop. 0 times 0. And more importantly, just what's the slope of 2? 0. That's all taking a derivative means. So what's the derivative of any constant? 0. Okay, I like it. I like it. So real quick, I'll do this sometimes. What if my function was this? What's the h prime? What's h prime? All right, you're taking too long. You're taking too long.
Pi to the equal.
Nope, stop. Nope, nope.
It stays the same.
Zero, the derivative is zero, because pi to the e is a constant, natural log of cosine of e is a constant. So h of x is a constant, yes? You guys see that? Do you see any x dependence?
No.
What does it mean if there's no x dependence? It's a freaking constant, yes? Is it like a nice constant? No, that's why if I take the derivative, it's nice that it becomes zero. You guys see that? Yes, I will be an asshole. No, all right, so real quick. What is, if I had this function here, f of x is 7, what's its derivative? Why?
Because x to the 0 would be 0.
Because you can even ask yourself this, how much does 7 change as you change x? It don't. So of course its derivative is 0, because it's tracking how much it changes as x changes, yes? So f of x is 7. What if I make it x 3? What's f of x?
0, sorry.
Still 7.
F of x is 7. So what if I make x 3? What's f of x? 7. What if I make x a billion? 7. So does it ever change? So what's its slope then? 0. What's the rate of change of it? 0. So if you are looking at a constant, now why is that a constant? How do you know that's a constant? Because it doesn't have an x. Does this have an x? Does it have a variable? Even better. Does it have the variable in it? Does it change then as I change x? Alright, same shit. It's 0. It's a constant. Yes? I'm not going to do that a lot. I'm going to do it. You're going to see like e to the pi minus e to blah 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 over the next one blah blah blah. 0. The derivative is 0. Okay, maybe. Okay. No, I won't reconsider.
Is there work you gotta relate to that?
Nope. Sure. Because what work do you have to show here? Yeah, it's a constant. It's a constant. And we know that the derivative of any constant is 0. So if I put on your show work, you're allowed to come kick me in the leg. Because you don't have to show any work for that. It's a constant. Okay. So, one more thing I want to point out. I can't remember if we actually talked about this, but there was this thing that showed up in the homework. And if you make a table of values, later this semester we'll actually be able to prove this. But this limit is 1. Oh, I did talk about this a little bit. Because it's about pendulums and small angles. It's about the same height. Okay. So, watch this. Let me see. Let me see if I can push my luck. Just to do this a little bit early. What if I had this function? By the way, what does this function look like? Yeah, where does it start? 0. And then it goes up and down and up and down and up and down and just forever. Poor little guy. We created him like, keep doing that. What do I do? You do this. Oh. Keep that in mind. Now, I want to know the derivative of this. What do I have to use? Is this in the form of x to the n? So not. So not. So what do I have to use?
The formula there.
Limit definition. F of x plus h minus f of x divided by h, yes? I love this for so many reasons. Of course you would, John. Is there anything you could do to that? Can you, oh dear God, can you distribute the sign? Of course not. Of course you can't. Does this say sine times x plus h? What's the right way to read this? Sine of x plus h. You can't distribute this because it's not multiplying. That doesn't make any sense, yes? So don't do that stuff and say it's 1. No. Or sine h over h. No. Okay. Does anyone remember what the sign of a plus b is? There's an identity. Anyway, if you ever, all right. Anybody? Ooh. Huh?
2 sine A.
Okay. This is sine A cosine B plus sine B cosine A. Does that sound at all familiar? A little bit? Okay. Real quick, cosine of A plus B. Does anyone remember that now that that's sort of like dredging up some old trig stuff? By the way, I say cosine is an asshole. Cosine, when I teach trig, and this semester I'm going to bring it up again because he's going to continue to be an asshole. Cosine is always an asshole. Look at sine. Look what he did. Sine A plus B. Hey, cosine, help me out. I'll do this one, you do that one. We'll keep the sign the same, and then I'll do that when you do this one. Yeah, let's cooperate, cosine, because like whatever. Because cosine's an asshole. So what does cosine do? Cosine says, oh look, I got some toys. Me first, screw you, sine, screw you, plus, screw your plus. All right, sine, you get to play with the shit because now I'm done. Okay. Now, everything I just said is not mathematical. It's a story I made up. But it's crazy how much that applies, that cosine is an asshole. Does everybody kind of see that? It's just a way to remember what's going on. Yeah, just another way to memorize this shit. Yes? Hell yeah. I don't even have that memorized. I never make my students memorize that because it doesn't come up as often. Yeah. But there is a tan A plus B. I mean, you could just divide those two, but then you can simplify it. And I'm not going to do it. So, help me out. What would sine of x plus h be then? Sine x, cosine h, because they take turns. Cosine's a nice guy. Keeps the sign the same. Sine h, cosine x. Yeah. So you just switch the thing they're playing with at the moment, right? Is everybody semi with me? Okay. So now, and again, this is the construction approach. What I'm looking at needs this. Okay, let me build that, and then I can shove it in. Yes? Bless you. Real quick, if I let h go to 0, what does cosine h do? If the input's going to 0, what is cosine approaching? What's cosine of 0? 1. Yes? Cosine of 0 is 1. Does everybody see that piece? Because I can put h to 0 and whatever, so I'm going to put it right here. If I let h go to 0 for this guy, this goes to 1, so this goes to sine x. Sine x times 1, right? This goes to 1. Therefore, this and this cancel. Yes? Yes? If h is going to 0, cosine goes to 1. Sine x minus sine x is 0. So then I'm left with this. I'm going to write it like this because I'm weird. What is the limit as x goes to 0 of sine x over x? We just said it earlier. 1. So what's the limit as h goes to 0 of sine h over h? 1. So this is cosine. Now, real quick. I was debating earlier whether I wanted to do what I'm about to do first or second, and apparently I decided to do a second. What did we just figure out, by the way? If I have sine, its derivative, oops, I'll show you that in a minute, is cosine. Look back up here. What's the slope here? 0, and that's pi over 2, yes? So if I'm going to graph the slope, something that a lot of us should come see me about, that slope is 0, so I'm going to put a 0 right where that is because I am graphing the slope. What's the slope here? Positive, but getting smaller, yes? Okay. And what's the slope here? Let's start back here at 0 also, right? And the slope is positive, getting bigger, yes? Positive, getting bigger, and then it's positive, getting smaller until it gets to 0. And then it just kind of continues. What did I just draw?
The
Frickin' cosine. So that's why the derivative of sine is cosine. Now, graphically is not a proof, but it does verify that it makes sense that I got cosine. Because if I graph the slope of the dumb thing, I get something that looks like cosine. Maybe? Screw you, Jeff. Okay, so. Now, what's interesting is, if I do this whole thing for cosine, its derivative comes out to be negative sine. Cosine, once again, being an asshole. Damn it, cosine. What the shit? So I could do the whole limit definition, we could do blah blah, and it would end up with negative sine x is the answer. Okay. So let me give you this paper. It's got basically everything we just talked about. Where is it, Jeff? Over here. And it's got some practice problems I want you guys to try. Everybody now. So it's got our little proof up here, just written better. Yes. It's got the rules we actually went over during our discussion. It's got the derivative of sine we just did. I want you to go ahead and, this is a little early, by the way. We don't do trig functions until section 3.3, I think. I just wanted to, I don't know, I just couldn't help but show you. Try to do these out real quick. Just on number one, just try those on number one. You can work with people near you if you want to. That's just the thing we know. You can set up a table. Yeah. Cool. So as long as the thing is going to 0, that ratio will be 1 in the limit. Yeah. And do you have a calculator right there? Do you have a calculator? Oh, yeah. Yes. So do sine of 0.001. Oh, that might be a little small. That means when the decimal value is so 0.00099, you round it up as 0.00. So if the input's really small, the output is roughly the same. The closer you get to 0, the more sine x becomes x. That's why the ratio is 1, because they become each other. Yeah. Something I was going to do. So number one is pretty much you get it or you don't, right? The only thing on number one you have to rewrite is which one? You know, you have to rewrite it before you do the derivative. Which one? F. It's in the radical notation with subs. Radical notation, just subs. Let me know if you're having any trouble. So, how would you rewrite it?
Can I ask a question? For answers, if you get an exponent, like a negative exponent, do you want it rewritten as a positive exponent?
No. It's generally better, most of the time, to write it up top with the negative power, right? Now, sometimes it might be better not to, but most of the time it is better. Oh my God. Oh. This stuff is a cheap high right there, man. Jeez. Alright. So like I said, so you get it or you don't. So what would this be?
5x to the fourth.
Yeah, 5 comes down, x to the fourth, I like it. This one?
Negative 33.
Yeah, the negative 3's there, so this comes down, makes it negative 33, and then the power goes
10.
to 10, 1 down by 1. This one, of course, is the teacher's favorite, 4 problems in 1.
16x to the seventh.
And again, you could look at this whole thing, what's the slope of 2x minus 9?
Plus 2.
2, yeah, see? Sometimes you have to step out of the problem to realize, oh, that part's just freaking, what's the slope of that? It's just 2. The slope of any constant, 0. That's why that's gone. And the slope of 2x to the first, 1 comes down, blah, 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 blah. You can do it that way, but that way takes forever. This one's the same as all of them, it just has a negative. What do you think is the most common mistake for somebody to do right there?
Adding
Yeah,
that
they'll put negative 2.
minus 1.
You gotta go down, not up. Okay. But again, we're human. You're gonna do that. Have I done that? Hell yeah, I've done that shit. And then I'll catch you later. What the hell is that? This one?
2.
By the way, do you guys see that is not 2 over x cubed? Can you guys see that? Alright, someday I'm gonna figure out how to write that so that everybody can see that is not 2 over x cubed. The bar would be bigger, yes? That is x to the 2/3. So 2/3 comes down. X to the negative 1/3. Kick ass. And then, how do I rewrite this?
X to
I put it here. X to the
9/7.
9/7, and then the derivative would be 9/7. X to the,
Negative 2.
no, careful, positive 2/7. 9 minus 7 is 2. Yeah, if the power is bigger than 1, it's going to end up being positive after the derivative, right? Okay. And by the way, I kind of, as I'm doing this, I'm like, I really need to rewrite this because I don't like the way I've done this, because you guys really need to get used to being nice to yourself. So here, if y is 5x to the negative 3, then y prime is negative 15x to the negative 4, yes? And as it shows at the top of this, The other way to write prime is in this notation. This means the difference in y as x changes is this. This notation is actually better. This is quicker, this is better. If y was peaches and x was years, this would be peaches per year. I could see the units on the answer from the notation, yes? So it's better. Why do we use this more often? Because it's quicker to write, yes?
So it's the same thing. just-
These both mean the exact same thing.
Just like on the second one, you can see the ratio of the velocity.
Yeah, it's a ratio, it's in your face, it's freaking slope because it's changing y over changing x. I can see the units. Y prime, I get none of that. But it's quicker to write. So that's why we do this more often. Okay. I'm gonna try to remember to incorporate this more often because this becomes more important later. At the beginning, you're like, why would I ever worry about this shit? Later, you're like, oh yeah, that's why I worry about this shit. Okay. Anybody tried number 2 out yet? I know I didn't say you to, but I think a few of you guys tried it. What's the one thing you have to be careful about before you do anything? And actually, let me ask you this. What am I gonna do? How do I find the equation of the tangent line?
X negative y.
What 2 things do I need for the equation of a line?
Slope.
Slope and a point. I gave you a point. So I gotta find the slope. And of course for us, slope means
F prime.
take the derivative. What if, before I take a derivative, what do I have to rewrite?
X
That-
negative y.
Negative 2x.
How do I rewrite 2 over x?
2x to the negative 1.
Kick ass, because negative power just means flip. Right? 4-letter word you can say in mixed company. So then, go for it. Find the slope of that function at that point. That's the first step. Of course, once you get the slope, try to do y minus y1 equals m times x times x1. Get the equation of the line. Or m is supposed to be if you like that better. So what's the derivative? 12x cubed plus 2x to the negative 2. So how do I get m? How do I get the slope?
It's prime of 2.
Good. I plug a 2 because that's where I want to know things. I plug a 2 into my slope function, my derivative. If I plug a 2 into my derivative, it'll tell me the slope at x equals 2. And when you do that, you get 12 times 8 plus, what is that, 2 fourths. So you get 96.5.
I have it right. I just did it differently.
You didn't trust it?
No, I did it differently.
Oh, okay. But you got the right answer.
Yeah.
So that's my slope. So how do I piece together my line? Y minus the y piece equals the slope times x minus the x piece. And then you distribute, blah, blah, blah. I just don't care. Right, you should solve for y.
I'm gonna get 47.
Is that alright? Does anybody need to see that shit? Let's see. So you get y equals 96.5 x. Jeff, what are you doing, buddy? 96.5 times 2 is 193.
193, yeah.
And then I add the 47. So I get 96.5 x minus 146.
Yes.
Go, Jeff, go. that okay? Last couple steps there were just distribute, add the 47, whoop-de-doo, right? So if you need the equation of the tangent line, take the derivative, plug your x value into the slope, get your point, blah. This process, when are we going to stop doing this? Never. It's going to be forever in this whole class. This is the most commonly asked question. Every time we learn a new derivative rule, you're going to get a find the equation of the line. It's a tangent of x plus 7. You know, you take the derivative using the new rule. You're going to see this question a lot. So just get used to it.
Can you zoom out a little bit?
Yeah. So what about number 3? What's up with number 3?
You find the derivative and you can just.
Yeah, because what does it mean for the tangent line to be horizontal? The slope would be 0. Yes? Slope equals 0. Slope is derivative, so if I take the derivative, I would then set it equal to 0. Go for it. I can't remember if I said this in this class, but when I say where is something happening, that's x. So the locations of where something is x values.
Life support.
Life support, exactly. I didn't see anybody come in on the 30. Okay, this time. The class next door was pinging us. So when you take the derivative, what kind of function do you get? Well, let's do this. What's the derivative? 3x squared. 12x minus 63, and I want to set that equal to. Now, dear God, before you start doing quadratic formula or whatever bullshit, if that first number was a 1, it'd be really easy to factor it. Can you make the first number a 1? Yeah, of course, you can divide by 3. Everything is divisible by 3, yes? And then screw quadratic formula. Let's see if we can factor the damn thing, right? Okay. Divide everything by 3. Can you factor that? Can't factor 21 too many ways, so which way makes 4? Factors that multiply to be 21 and add to be 4. 7 and 3. Which one is positive?
7.
7 to make the middle positive. Boop, boop. So then what are my 2x values? Negative 7. Positive 3. So at those x values, the slope of the function would be 0. It would be a turning point, yes? Okay. Or, I've got to be more careful. Or it could be a resting point. So a parabola would go, but a cubic would go, yes? But it's still 0 right there, correct? So it could be the turning point, or it could be like a little prank it's playing. I'm gonna turn, no I'm not. Sort of like unemployment, oh good, oh shit. Right? It's a possible future. Okay. Go, economy, go. Okay. How do you guys feel about this new stuff today? It's a little more, you can sink your teeth into it a little more than limit definition and stuff. Yes? You can actually get in there and do some stuff. Okay. So, what I want you to do now, I kind of want, well, we'll see if you guys, I don't like forcing groups to happen, but I want you to work on this side. There's a guys all did this one perfectly fine.
Yeah, that's just
Some of you guys did too much, but I don't blame you because you felt like there wasn't. But this is all you could do. This is it. Leave the bottom factored so that at the end you can tell if anything cancels and nothing does, so you're done. Just to let you know, this is the second step in a calculus problem. This is an actual answer to a derivative of a funky ass little function. This happens all the time in calculus. Do you guys know what Math 178 is here? It's business calc, essentially, is what we call it for shorthand. In that class especially, people get to calculus pretty well. Normally the first step is calculus, and the next 4 or 7 steps is algebra. They'll get the first step, and they'll die on the next set of steps. So most of what you're going to do in here is algebra. Like the first or second step is going to be calculus, and then algebra. Yes. Okay. So this is just algebra because I did the calculus for you on these. So now here you distribute. So 4 cosine sine 4 plus 4x cosine x. You're not gonna have room for this, Jeff. That's a good point, Jeff. Here. All right, let me just devote all this shit to this. Okay, so I get 4x. I'm sorry, I did that too soon. 4 cosine x sine x plus 4x cosine x. I'm still not gonna have enough room. Minus 4x sine squared x minus 4x squared sine x. Well, here, so on these, I'm going to kind of line things up. This will be minus 4x cosine squared x. I'm going to put that here for some reason. And then it's minus 4x cosine x, and that goes right there. See? All over barf. Okay. You guys see what it did? These, you can see why I lined them up. They're like terms. Why did I line these up?
Because they're opposite.
If you take a negative 4x out, so let me write that one. 4 cosine x sine x. This is dead. If I take a negative 4x out of these two, what am I left with? Sine squared plus cosine squared. What is sine squared plus cosine squared? What's sine squared plus cosine squared? What's sine squared plus cosine squared?
1.
1. Where's sine come from? What's that thing you have to draw and you have to fill in the blanks in trigonometry?
Circle.
Unit circle, yes? Go with me for a second. Unit circle, why is it called a unit circle? Because the radius is... Okay. What do you think the number is that we call the unit? 1, because it's 1 unit, yes? So unit circle has a radius of 1. This would be equal to cosine. This would be equal to sine. I really want you guys with me. What's the definition of cosine? Give me any definition of cosine. X value divided by hypotenuse. Or you could say adjacent divided by hypotenuse if you want to be silly. Sorry. If you learn SOHCAHTOA, great. It just sucks. Is everybody with me? What did I just say the hypotenuse is in a unit circle?
X.
1. So this is cosine x. This is sine x. Yes? So what's cosine squared x plus sine squared x? 1. Good old Greek dude, Pythagorean theorem, yes? That's all that dumb thing is. That's why they call the Pythagorean identities. You got the other one that's 1 plus tangent squared equals secant squared, and 1 plus cotangent squared is cosecant squared. Does sound all familiar? Those are the 3 Pythagorean identities. You can get all of them if I divide by cosine squared. Isn't that 1? Isn't that tangent squared? And what's 1 divided by cosine squared? Secant squared. So 1 plus tangent squared is secant squared. I can create the other 2 starting with sine squared plus cosine squared equals 1. Everything I just said doesn't make sense. You've got to focus on identities. Trig is going to come up. I teach 180. You could teach 180 have very little trig in it. I make sure to have a decent amount of trig Because if you're going to take Calc 2, how many are planning to take Calc 2? Okay, you ready for this? I don't mean to scare you. But a huge chunk of Chapter 7 is trig. So can you imagine somebody teaching 180, doing very little trig, and then a student does well, Calc 2? Here's Calc 2. They didn't do that. Yes? So I'm trying to soften that. Keep the trig alive so that when you hit Calc 2, it's more like this. Oh. You kind of with me? Not the brick wall it could be. Okay. Sorry. I just want you to appreciate the trig I'm trying to throw at you. Yes.
In that first step, the only thing that cancels is the 4x.
Exactly. Yeah, nothing else is like terms, right? You all cool with these are different?
Yes.
Here I have 2 signs, here I have 2 x's. Yeah. So this would become 1. So then I just get this minus 4x minus 4x squared. I just get that. There's nothing I can do. There's nothing I can simplify. Too bad for me. Is that okay? I'll take that as a no, but we'll see if anybody has specific questions. This is a very classic example. You're going to be doing this kind of thing a ton. This is not going to happen as often, but when you see squared trig functions running around, you think, is there a Pythagorean identity in there? Because that could simplify a lot of shit. So when you see squared trig, sine squared, cosine squared, tangent squared, whatever, you're like, oh, wait a minute, is there a trig identity I can use? So what should you have sitting next to you as you do your homework? A frickin' thing of trig identities. If you don't have such a thing, ask me. Or I think I put it up in Canvas, didn't I? Don't I have trig laws up in Canvas? Who's been in Canvas? You guys are like, you don't put grades in Canvas, Jeff, so I don't look at it. All right. So let me know. I'm pretty sure I did. It's a green
I
sheet
think
of
there
trig
is.
laws. Okay. Yeah, good. I'm gonna let us out at 2:30, by the way, if you didn't hear me say that earlier. So be excited about that for one day. For one day. This one, okay, this is maybe a little early, but it's fine, because we should have talked about inside functions. Do you get the idea of an inside function? I mean, it's literally, even if I didn't explain it, you should be able to kind of pick up on what I mean. For example, what's the inside function here? H of x is composed of
3x.
a couple of things, yeah. 3x squared minus 5x. What's the outside function?
The raised to the 5th power.
5th power. So you can easily identify the inside and the outside. For some reason, that's going to become very important, and it's when we get to something called chain rule.
Yes, my favorite.
Yes, very often it's students' favorites. Heavy sarcasm. What's the inside function here?
The x squared.
Drag minus, and what's the outside function?
ln.
And does that make sense? If you had to say something is inside something else, you would say, oh, that shit's inside ln. Okay, bam. What about this one? Sine x is the inside, and the outside is e to a power. So that skill by itself is going to feed into a calculus process. So the better able you are to identify what the inside and the outside are, the easier the calculus is going to be. Those are 2 separate skills and they go together. What about here?
I'll bring that up first.
Okay, x squared plus 3 is inside what?
1/3 of x.
Is inside the square root, which is inside, yeah, I like it, 1/, stuff. So this is inside a root, which is inside a 1/, stuff. You guys see that? So you can argue that this is like a Russian nesting doll. What's the innermost doll? X squared plus 2. What's the middle doll? Square root. What's the outer doll? 1/, stuff. Maybe? Screw you, Jeff? Now, if I rewrote this, it'd be a lot more straightforward. How do I rewrite this? X squared plus 3 to the... Now what's the inside? X squared plus 3. And what is it inside of? -1/2 power, which I think somebody was trying to tell me earlier, and I just discounted you for just a bit. And this one, I don't know why I put this here, because it's the same as this one. I mean, what's the inside function? 3x minus cosecant x. What's the outside? Tangent stuff. Do you guys see the difference between this function and this function? Do you guys see the difference? 3x minus cosecant is inside tangent. 3x minus cosecant x is multiplying tangent x. Completely different functions. If I had to do calculus to them, it would be completely different rules I would be using. Because this one is a product, yes? That function times that function. So I'm probably going to use something called a product rule. This one is shit inside of this dude. We don't have a shit inside of this dude rule. This is what we call the chain rule, but we don't have to know that yet. Okay. Not too bad, right? That by itself, not too bad. Then you have to apply the calculus. Okay, so last thing for today, my last 10 minutes here. Any questions over everything we just did? We just did a decent chunk of stuff here. So up here is just simplification. But the most important thing is to not cancel those. No. Problem becomes a lot easier, but it becomes wrong really quick. So if you're just trying to get done, you'll be done quick. You'll be wrong. Okay. Last thing. This is kind of a big thing. Let's see. So we know, for example, we know how to take the derivative of that, yes? What's the derivative of that?
Negative sign.
No.
Oh, cosine x.
Cosine x. Is that cool?
Cosine x. Negative
Yes?
sign.
We know how to take the derivative of this. What's this guy's derivative?
2x.
2x. Yes? So this is nice. This is nice. What if I had to take the derivative of this? You guys see how that is more complicated. It isn't x squared plus sine x, because that wouldn't be a big deal at all. That'd be 2x plus cosine x, because then I could take the, but derivatives don't distribute across multiplication. Nothing really does. Right? So that's not how this works. I gotta take the derivative of that function. And what is this primarily? It is the what of two functions I know stuff about. It's the product of two functions, yes? So ready to get the basic premise. I know how to take the derivative of that piece, and I know how to take the derivative of that piece, but when I multiply them, I get this brand new function that's got parts I know, but I don't know what the whole thing does. That is an issue. So you cannot just go 2x cosine x. Yeah. No, that's bullshit. That is bullshit. I really want that understood. So when it's a product, I've created a new function, but it's got parts that I know stuff about. Okay. So what I'm gonna do, let me see. I'm gonna try to stick to my promise. Oh, shit and a half. Sorry, guys. That was out of nowhere. If I lean over that way at all, oh, that did exactly the opposite of what I wanted. I have destroyed this whole thing. Go away. Thank you. Okay, that was exciting. So I want to do the derivative of a function that is a product of two functions. So if I want to investigate that, I have to go, H was a bad choice, but you guys will be okay. This is a different H, yes. Let me see if you guys are cool with this. Is that cool? Because don't I plug an x plus h into what I'm looking at, minus plug an x in what I'm looking at? Are you guys all with me? That's the rule, right? That's how the limit definition works. And what's the limit definition? It's algebra. Okay. So what the shit, what do we do? I don't know. So I'm about to do something that I would never expect any of you to come up with, because this was come up with, again, in the same time as Pascal earlier, where all he had was candles and paper. So like, so something you would never ever, well, I don't want to say that because maybe you would, but it's so trippy. This is like the first place you guys see this. All right. There ain't shit I could do here. Y'all agree with me? There's what the hell would I do with this shit? Well, here's what I'm gonna do. I'm gonna turn my paper because I'm gonna need to have some more room. I'm gonna do something really weird, and as I talk, I'm actually trying to remember exactly how it looks. Let me see. It's been a while since I did this. Yeah, okay, that's perfect, Jeff. I'm gonna have to zoom out a bit. Let me see if I can keep you guys with it. That's a lot more than I had, yes? What did I just do? I just did nothing. I did absolutely nothing. Because didn't I add 0? So I did nothing. What's this plus this?
No.
0. So I just added 0. It's sort of like multiplying top and bottom of a fraction to make it look different, but you really just did nothing. You multiply by 1. Ooh. So I added 0. Ooh. Doesn't that seem stupid? Good job, Jeff. You put more shit in there. But what can I take out of these two? I'm going to kind of split this up. I really want you guys with me. You guys, that's there, yes? That's there? That's there, yes? That's there, yes? What I put in the middle? Minus something plus same thing. So did I just change anything? What's 5? Isn't 5 plus 1 minus 1?
Yeah.
Yes. Why would you put the plus 1 minus 1? I don't know. In this case, it's useful. This kind of thing happens all the time in math. Add something, subtract the same thing, and then I'm able to do shit. What can you take out of the first two? The first two.
Gx plus h.
Yes, g of x plus h. So I'm going to write Jeff and a half. Screw it. I'm going to let it stay. Sorry, guys. I need a guard around this thing. Okay. Whoops. All right. I'm going to write it like this. F of x plus h minus f of x over h. And I'm going to take the g of x plus h out. Is that cool? You told me to take a g of x plus h out, so I did. I just took it out on that side. Is that all right? Plus, what comes out of this top? F of x, and then what's left? G of x plus h minus g of x over h. What the shit is this? What is the limit of this? What is this the definition of? F prime. And what do I get when I let h go to 0 here?
G prime.
G.
Oh, G.
G of x, yeah. And then over here, I get 8 f of x, right?
G prime.
As h goes to 0, f of x don't care. And what is this the definition of? G prime.
G prime of it.
So if I have a product, derivative of the first piece times the second plus the first piece times the derivative of the second. So the problem we were just looking at, if I had x squared sine x, its derivative would be derivative of the first piece times the second plus the first piece times the derivative of the second. Do you see how each function gets its own term? Why? Because it does. We proved it. So when I have a product, derivative of the first times the second plus the first times the derivative of the second, they each get a term. I'm making a major emphasis on they each get a term because every rule we're going to learn has that same idea in it. They each get their own term. So when we learn quotient rule, chain rule, I'm going to bring that shit up again. Hey, look, they each get their own term. Okay. And what would you get? What's the derivative of x squared? 2x. And what's the derivative of sine x? Cosine x. So that's your answer. That's what the derivative of that function. It should be more complicated because it's the product of two functions. It should make a more complicated function. So I should expect the derivative to be a little more complicated. Now obviously that's a very quick little foray into product rule. Yes? And then we still have to develop quotient rule. But I'm going to stop. I'm going to stick to my promise, stop messing with the lights, and we'll end class. Now. Thank you. Don't forget, you can get help with your test corrections. You can ask me if they look good. You can ask me for help. It's crazy. Yeah.